Welcome to This Explainer. Today, we're going to demystify statistical formulas and build up your mathematical toolkit step by step. If you've ever looked at a page full of sigmas, variables, and subscripts and felt totally overwhelmed, don't worry. We're going to translate those daunting equations into simple, actionable logic that you can apply to literally any data set.
Look, no matter how complex the equations seem on the surface, calculating the arithmetic mean, which is represented by that x with a little bar over it, is simply about finding the exact mathematical center of your data. It's the balancing point. Every single formula we're looking at today is just a different pathway to arrive at that exact same destination, completely tailored to how your data happens to be organized.
Here's our agenda for today. We'll be climbing the ladder of complexity across 4 steps: individual series, frequency array, frequency distribution, and finally, the weighted mean.
Step 1. Individual series. This is the foundation of the mean.
Let's start with data in its rawest form, just a simple, ungrouped list of numbers. Here is your most basic recipe, the direct method. The formula is x bar equals sigma x over n. In plain English, that big Greek letter sigma just means the sum of. So you're looking at the sum of your individual observations, the x, divided by your total count of numbers, which is the n.
In practice, this is really just 2 straightforward steps. First, add everything up to get your grand total, or sigma x. Second, divide that total by the number of items, n. If you have 5 test scores, you add them all together and divide by 5. Super simple, right?
Now, notice the contrast here. The direct method is fantastic for small, manageable datasets. But what if your numbers are huge and clunky? Imagine calculating the average income of 1,000 different households. That's when we pull out a new tool, the shortcut method, which introduces the concept of an assumed mean, or A. By picking an assumed mean first, which is basically making a highly educated guess at the center, we only have to calculate the smaller deviations, or D, from that anchor. You just subtract your assumed mean from each observation. Then, add up those tiny deviations, divide by n, and add it back to your assumed mean. It makes the math incredibly easy to manage, even if you're doing it by hand.
Moving right along to step 2, frequency array. It's time to add the F factor.
As we move up the ladder, what happens when specific observations appear multiple times? Writing out 100 identical numbers is highly inefficient. So instead, we use a frequency array. We now have an F column for frequency. It tells us exactly how many times each X value occurs. If the value 50 appears 10 times, you just write 50 under X and 10 under F. Notice how our base formulas gently adapt to this new layout. For the direct method, instead of just summing x, we first multiply each observation by its frequency, giving us fx, and then we sum that up. Then divide by the sum of the frequencies, which is our new n. And for the shortcut method, we do the exact same thing with our deviations. Just multiply them by their frequency first to get fd before summing.
Now, there's an even sharper tool here, the step deviation method. If your deviations happen to share a common factor, let's say they're all multiples of 10, you can divide them by that common factor, c. This shrinks your numbers down to step deviations, or d prime. You do your multiplications, sum it up, divide by total frequency, and then just multiply the whole fraction back by c at the very end to scale it back up. It's a real game changer for keeping your calculations clean.
All right, step 3, frequency distribution. Let's master class intervals.
Reaching the 3rd rung of our ladder, our data isn't an exact number anymore. It's grouped into ranges. Here's what a continuous distribution looks like. Look at that first row. 30 people fall into the age interval of 10 to 20. Because we don't know their exact ages, we have to find a representative number. That's where the mid value, or m, comes in. Right in the middle of 10 and 20 is 15. So that 15 now stands in for all 30 people in that group.
Because we swapped our exact x observations for these new mid-values, our base formula gracefully evolves. We simply replace the x with an m. The direct method becomes the sum of frequency times mid-value divided by the total frequency. The core logic remains entirely untouched. We just change the variable to fit the data's shape.
The exact same logic applies if you want to use the shortcut method here. It operates just like it did before to keep your numbers small. The only difference is you're calculating your deviations directly from those new mid-values. So d becomes m minus a. From there, multiply by frequency, sum it up, and plug it right into the formula.
And if you use the step deviation trick for continuous distributions, there's a built-in advantage. That common factor c naturally becomes the size of your class interval. In our previous age table, the interval was 10. So you divide your deviations by 10,
Work with those tiny, single-digit numbers, and then multiply by 10 at the end. It keeps the math wonderfully balanced and incredibly fast.
Finally, step 4, weighted mean. This is for when some data matters more. We've reached the top of the ladder. Now, standard averages assume every data point has an equal voice. But what if you're calculating something like a final grade, where a final exam is worth way more than a weekly quiz? Looking at this dataset, we see each X observation is accompanied not by a frequency, but by a W, a specific weight of importance. For instance, the observation 20 carries a hefty weight of 10, while the observation 10 only carries a weight of 4. We absolutely cannot treat these equally. The math here beautifully mirrors the frequency array we saw earlier. By just multiplying the values by their weights, giving us Wx, and summing those up, we capture the total weighted value. Then, instead of dividing by the number of items, we divide by the total sum of the weights. We easily find a mean that mathematically respects the assigned importance of every single item. So take a step back and look at what we've covered today. Whether you use a straightforward direct sum, an assumed mean to trim down large numbers, or a weighted fraction to balance importance, never forget the big picture. Every single formula we just explored is simply a different, specialized tool designed to do one thing: find the exact center of your data. You've mastered the arithmetic mean, and you now have the step-by-step tools to calculate it no matter how the data is thrown at you. But this leads to a fascinating final question. As we look at the overarching formula, mode equals 3 times median minus 2 times the mean, how do the median and mode complete this statistical picture? Are there datasets out there where the mean actually paints a misleading picture of the center? Well, that is a puzzle for next time. Keep exploring those numbers.